So last time we talked about the reduction of order. So we know how to solve, high order linear differential equations. We know we need to find general solutions for the associated homogeneous equation first. So that means you put the 0 on the right side. Okay, all the derivatives of y and y itself will be on the left, and the remaining thing is on put to the right side. And then if you change this right side to 0, then that's called the homogeneous equation. So we want to find the general solution for the associated homogeneous equation, and we need to find the one particular solution for the original non-homogeneous equation and add them up. And that's how we solve a general non-homogeneous linear RO differential equation. And then specifically for second order linear differential equation, then we need to find the two linear independent solutions for the associated homogeneous equation to make a fundamental set. So this reduction of order is about how to find the second linearly independent solution if you already find one solution for the associated linear equation. Okay, how do you find the second one, linearly independent, the first solution? So it turns out that we can write, the second solution y2, which we don't know, as some function u times y1, which we already found. Okay, then we can use that substitution into the differential equation and change the problem into a linear differential equation of first order. And then we just derived the formula for it. The whole thing is just involves a bunch of integrals. Okay, so if you look at the last formula on the bottom line, y2 is just equal to y1 times the integral of e to the negative integral p over y1 squared. Okay. So y1 squared we already found. P is just from the differential equation in the standard form. So we just plug in those functions and integrate to get the y2. All right. But remember, you have to write the differential equation in standard form to start. Okay. Just remind you of that. So I'm not going to repeat the whole derivation of the formula. Let's just do one example to use the formula to find the second solution linearly independent of the solution we already have for the associated homogeneous equation. All right. So in this example, we have the differential equation of x squared y double prime minus 7xy prime plus 16y equal to 0. And it is given that y1 equal to x to the fourth is a solution to this equation. So we need to find another solution to the equation linearly independent of y1. By the way, we're going to discuss how to find the y1 later. Okay. So then if we know how to find the y1, then we can find the y2 by using this formula in here. And then find the general solution of the associated homogeneous equation. Okay. In this example, the equation is already in standard form, not in standard form, but the homogeneous equation. Okay, so we don't have to change it. But the equation itself is not standard. Okay, we have x squared as the coefficient for the y double prime. So we need to divide by x squared on both sides to make it standard. All right. So if you do that, you just divide the equation by x squared on both sides, and that will give us y double prime minus 7 over x, y prime plus 16 over x squared. Because you remember you have to divide by x squared for each term on the left, and in the second term, one of the x will be canceled. So that's why we get the 1 over 7 over x. And then you can just read p is just negative 7 over x is the coefficient function for y prime by definition. Okay. And the formula for y2 is just y1 times the integral of e to the negative integral p over y1 squared. That's what we obtained on last page. So y1 is x to the fourth. Plug in, and p is negative 7 over x. Okay. So do a little simplification inside the integral. X to the fourth squared, just x to the 8th. Remember, you multiply 4 and 2, get 8. And 2 negative signs on the top of the exponent of the exponential. So we got the 7 that can be taken out from inside. So the exponent on the top is just 7 times the integral on 1 over x dx. Okay, so if we integrate 1 over x, you get the natural log of x. By the way, normally you should get the natural log of absolute x, but since we only want to find one of those y2, okay. So we just choose the function to be natural log of x, all right? And then we got the 7 in the front again, but that can be placed into the exponent for the x of the natural log. So that becomes e to the natural log of 7, x to 7. And once again, natural log and natural exponential compose to cancel the effect of each other. So at the end, we just got the x to 7 on the top, and then divided by x 8th at the bottom. So you get 1 over x inside the integral if we cancel x to 7. All right. So and then it's the integrate with the natural log of x again. You just you don't have to put the absolute value in here because we only need to find one of those functions. Okay. So so yeah, at the end, the solution is x to the fourth times the natural log of x, and that's independent of x to the fourth. If you do the Wronskian, okay, you'll find out that it will not be 0. So the Wronskian of y1 by 2, so they are linearly independent. So the whole idea of reduction order just change the second order equation to first order. But it is used to find the linearly independent solution of a given solution of the homogeneous equation. All right. So that's the end of this section. Any questions about this topic of this example? Okay, so if not, then we go to the next section for another topic. All right, 4.3. Okay, so in this section, we're going to discuss how to solve homogeneous linear equations with constant coefficients. Okay, so we're going to discuss the whole process of solving a homogeneous linear equation with constant coefficients. Okay, so what it means by homogeneous, again, the right-hand side of the equation is 0. So the general form of the second order linear homogeneous differential equation will be a y dot prime plus by prime plus cy equal to 0, where a, b, c are constants. Okay, so we talk about equations with constant coefficients. And then, we want to solve this equation from the start. Okay. So this is the first time we try to solve a higher order differential equation from the beginning. And the strategy or method here is we try to write the equation, write the solution y in the exponential form. So we let y equal to e times mx. Okay, you can always do that. There's nothing wrong with it. But the point is, if you think this equation itself, you have a, b, and c are constants, and you take the derivative y and the second derivative y, and then you add some term with constant times y itself equal to 0. So in order for that to happen, then you would assume, y should take exponential form. Okay. How do you get 0 if you take the derivative and second derivative of the function and add a term with the function itself? You get 0, and the function has to be in the form of exponential. Because when you take the derivative, you get the exponential function back. That's the only case when this can happen. So it makes sense, right? Although, for any solution, you can always write the function equals y times some, constant times exponential. But it's particularly true for this case. Okay, so it has to be in this form. In other words, okay. So then, when we take the derivative y, we get e to the mx back, but then you have to multiply the derivative mx, which is m. So that's m times e to the mx. And you take the derivative of y prime, you get y double prime. So once again, you have e to the mx back and multiply the derivative of mx, which is m. So that multiplies the m in the front, you get m squared. So y double prime is just m squared times e to the mx. Then you just plug in those y prime and y double prime, and try to simplify this equation a little bit. So then it becomes am squared e to the mx from y double prime plus bm e to the mx from y prime plus c times e to the mx. Y itself is just e to the mx. We assume the form. So that equals 0. Then all the terms have e to the mx that be cancelled. So at the end, we get the solution am squared plus bm plus c equal to 0. So that's just a simple quadratic equation. It's not the differential equation anymore. So that will determine what m is. Remember when we rewrite y equal to m e to the mx, we don't know what the m is. We know this solution has to take the form of e to the mx, but we don't know what m is. So this equation am squared plus bm plus c equals 0 actually gives us what m is. So we just solve the quadratic equation to get m and then plug into the solution of e to the mx, then we solve the differential equation easily, all right? Okay, so, but we have to consider different cases in here because depending on the quadratic equation, it can have real solutions or complex solutions. So we just split into 3 different cases, as we already know. So the first case is the quadratic equation has distinct real roots, m1 and m2. Okay, they are both real solutions, m1 and m2. So in that case, then we just got 2 solutions, y1 equals e to m1x and y2 equals e to m2x. And these 2 solutions, exponential functions e to the m1x and e to the m2x, they are linearly independent because m1 and m2 are not equal if you do the Ruskin of those 2 functions. So then the general solution or the solution of this differential equation we originally start. This is the linear combination of those 2 solutions. So that's C1 e to m1x plus C2 e to m2x. Okay. But if the quadratic equation am squared plus bm plus c equal to 0 has repeated real solution or roots, m1. So that means if m1 is equal to m2, then we only get one solution of e to the m1x for this differential equation. Then we need to find another solution linearly independent of this solution. And we already discussed the reduction of order on how to find the second linearly independent solution given one solution for the homogeneous equation. So if you follow that procedure using that formula, you're going to find another solution for the differential equation, which is x times e to m1x. So this solution is linearly independent of the first solution e to the m1x. If you do the Ruskins again, then the solution or general solution of the original homogeneous differential equation will be the linear combination of those 2 solutions, which is C1 e to the m1x plus C2x times e to the m1x. Okay. So that's different from the case 1. And the third case is when, of course, we got the 2 complex solutions for the m from the quadratic equation, m squared plus bm plus c equal to 0. those two solutions of M are conjugate because you just get plus and minus for the original part. Namely, alpha plus I beta and alpha minus I beta, they are conjugate to each other, and they are both solutions to the quadratic equation. So if you do the Wronskian of the two solutions, e to the alpha plus I beta x and e to the minus I beta x, they are linearly independent. The Wronskian is not zero. If you do that, so then the solution to the homogeneous differential equation would be the linear combination of these two functions, which is C1 e to the alpha plus I beta x plus C2 x times e to the alpha minus I beta x. Okay, so, but if you still know the Euler's identity, e to the I theta equals cosine theta plus I sine theta, then we can rewrite the solution in the other form of e to the alpha x times C1 cosine beta x plus C2 sine beta x. And here, C1 and C2 are different from the original solution in exponential form. Okay, so maybe I should write C1 prime, C2 prime. But anyway, those are just arbitrary constants. And the good part of this form of solution is that you don't see any complex functions in here. You know, although D1 and C2, they can be complex, you don't see complex functions in the form of the solution. Okay. So that's the third case. All right. Any questions? So if not, let's just do some examples. You know, now we can try to, or we can actually solve a second-order differential equation with constant coefficients. Okay, so that covers every aspect of the second-order linear homogeneous differential equation with constant coefficients. We can solve those equations completely. All right, there are three different cases. So let's try to solve the initial value problem 4y dot prime plus 4y prime plus 17y equal to 0 with the initial condition y of 0 equal to -1, y prime of 0 equal to 2. Remember, we have the initial condition here at x equal to 0. You know, you need two initial conditions actually to solve a second-order differential equation, and this is what exactly we have in here. The function value at the initial point x equal to 0 is -1. The derivative of the function at the initial point x equal to 0 is 2. So we can easily write down the auxiliary equation, which is the quadratic equation we obtained on the previous page. We call that the quadratic equation, the auxiliary equation. If you assume y equal to e to the mx and plug that into the differential equation, you're going to get this quadratic equation. So I'm not going to do it over for the derivation of this equation, but that's just a repetition of the process we had in the previous page. So then you just try to solve this M and this quadratic equation. We can use the quadratic formula. Negative b plus square root of b squared minus 4 times a times c over 2 times a. Okay, so we're a equals 4, b equals 4, and c equal to 17 in this equation. So plug in those numbers. So 4 squared is just 16. 4 times 4 times 17. What is it? 200 something. Okay. So if you just subtract them inside radically, you get negative 256. When you take the root of it, you get the 16i. Okay, so it's a negative number, so you should get the complex or imaginary number in here, and the bottom is just the 8, more than 2 and 4. So we got negative 4 plus or minus 16i over 8. That can be simplified to negative 1 plus 4i over 2. So what they do is just cancel 4 both on the top and the bottom. So you should cancel 4 on each term on the top and at the bottom. Okay. So 4 times 4 is 1. 4 divided by 4 is 1. 16 divided by 4 is 4. 8 divided by 4 is 2. Okay. So so this is KO3 we discussed on the last page. So the quadratic equation has conjugate complex roots, alpha plus r beta, where alpha is negative half and the beta is 4/2, which is 2. Okay, if you split this solution of M into the real and the imaginary part. So we get alpha equal to negative 1/2 and beta equal to 2, in other words. So then we can write the solution of the differential equation as well. Y equals e to the alpha x times c1 cosine beta x plus c2 sine beta x. That's the form we used in the case of complex roots for M. All right. You can also use the exponential form, but we usually use the real functions instead of complex functions. Okay. So that's the bottom 9 on this page, on the previous page. So then just plug in negative half for alpha on the 2. For beta, we got y equals e to negative half x times c1 cosine 2x plus c2 sine x. So that actually gives the solution of the differential equation. So we already solved the differential equation completely. But the problem is to solve the initial value problem. So we need to plug in the initial condition and find the C1, C2. All right. So the initial condition involves the derivative of y, so we need to take the derivative of this function. Okay. So again, this is a product of two functions. One function is the exponential function e to the negative 1/2 x, and the other function is c1 cosine 2x plus c2 sine x. So we can call this f and g. When you take the derivative of this function y, then we get y f prime times g plus f times g prime. Okay. So if you take the derivative of e to the negative 1/2 x, you can e to the negative 1/2 x times the derivative of negative half x, which is negative half, by the chain rule. And if you take the derivative cosine 2x, you get the negative sine 2x times derivative of 2x, which is 2. So the first term of the second part becomes negative 2 c1 sine 2x. So again, that's the chain rule. And similarly, when you take the derivative of sine 2x, you get a cosine 2x multiplied by derivative of 2x, which is 2. So that's 2c2 cosine 2x. Again, that's chain rule. So now we can plug in 0 for x and try to solve for c1, c2 from those two conditions. So if you do that, y of 0 equal to negative 1, so plug in 0 for x, so you get the either negative half times 0 times c1 cosine 0 plus c2 sine 0 equal to negative 1. And negative half times 0 is 0, and e to 0 is 1. Sine 0 is also 0. So then what's left? Just c1 times cosine 0, which is c1. We know cosine 0 equal to 1. So then we are got c1 equal to negative 1 immediately from this condition. And then the second condition says y prime 0 equal to 2. So now you just plug in 0 for x again into y prime. Okay, so the exponent, is again 0, and the cosine 0 equal to 1, sine 0 equal to 0 again. Okay, if you just do a little simplification, and then what you get is negative half c1 plus 2c2 equal to 2. All right, and so we can solve for c2 from this equation. If we move negative 1/2 c1 to the right, it becomes positive. But c1 is negative 1, we already solved. So plug in negative 1 for c1 and combine the terms on the right. We got 3/2, and so if we divide by 2, we get c2. So c2 will be 3/4. Okay. So at the end, the final result or the solution for the initial value problem is just y equal to e to negative half x times negative cosine 2x plus 3/4 sine 2x. If we plug in negative 1 for c1 and the 3/4 for c2. So that's the answer. Any questions? So we're going to finish this section next time.